about categorical boson-fermion correspondence.
Yeah, thank the organizer for inviting me, also for organizing this conference. So today I want to talk about the joint work with Mikhail Khovanov, which is work in progress. It's categorification of boson-fermion correspondence. So let me first make an introduction. So what boson-fermion correspondence tells is roughly it's the equivalent linear isomorphism of two vector spaces. So I call V sub B and V sub F. This is like bosonic Fock space. I'm sorry?
Anything else?
You saw? No?
Just wait.
Right here? Yeah. Okay. Okay. So VB stands for the bosonic Fock space. VF stands for the fermionic Fock space. So, okay, so you know this line is spanned by some called semi-infinite vector product. And this one is isomorphic to the polynomial ring together with like Q shift. Okay. This is just a linear isomorphism, and so the reason why this is called bosonic Fock space is because there is a Heisenberg action, and on here there is a Clifford algebra action. So this is a linear version of boson-fermion correspondence. So today's talk, I just want to categorify this picture as much as I could. So basically, I want to find some category which is fancy B and fancy F, such that if you take the ground group, I want you to recover the linear vector space, and for this correspondence, I want to find some equivalence of categories, and furthermore, you want to find some like Heisenberg category acting on that, and the Clifford category on that. So rather than just to have this isomorphism between vector spaces, you also have some like linear maps from the Heisenberg to Clifford, and also going back, okay, which is called like some vertex operators. You just you can express the generators of Heisenberg in terms of like some series written in terms of Clifford generator. So I also want to do this like categorical version of this correspondence. So before I move on, let me just mention some of the history of this. So I guess the first thing I'll mention is Heisenberg categorification, and then there's Tony's Savage. So some other, this Heisenberg categorification basically using the representation of symmetric groups, and Tony and Savage just generalized to the High group, High algebra. And then, so maybe more relevant to this talk is the later Todis and Kada has a paper about like categorification of vertex operators. So they're basically they interested in categorify the Heisenberg associated to ADE like type of quiver, and then they can also somehow categorify the map of theta, categorifying theta. So and later on, Todis and George Sousa so they basically do the same Heisenberg algebra as that, and also categorify a proposal categorification of the map theta. Namely, they want to have some functors in the Heisenberg algebra, and they can form some complex out of the Heisenberg generator, and they want to show like they satisfy the Clifford relation. So one of the Well, every student is working on this problem, just showing like they satisfy the categorical clipper. So there is another work on this boson-fermion correspondence by Franco. And Supernova, which is by studying the representations of SL infinity. So it's a close relative of the symmetric group in Michael's case. So this is just a brief history of this categorical boson-fermion correspondence. But my approach is a little bit different. So basically, they are all like a representation approach, namely starting from the Heisenberg side and try to find the clipper generator. So this talk, I'm gonna maybe starting from the clipper side. So let me first talk about clipper category. So this is more topological origin, so which is related to three-dimensional compact topology. Maybe a more familiar subject is this is like more gigabloors. So they are highly related to subject. Okay. So basically, the clipper category I'm gonna propose here is based on study the geometric structure in dimension 2+1. So before doing the categorical level, I want to first give you the linear version, which is a linear clipper action on the Fock space. Because I'm gonna use a different basis, so I want to write this very carefully. Okay. So first of all, what is VF? So VF is like K-span of semi infinite wedge product of even integers. So namely, I have some like monomials, which is written as M1 wedge, M2 wedge, M3, and so on. You require each Mi is an even integer, and also Mi will be 2i plus 2k for I sufficiently large. So it's going to be stable after finite time. Okay? So for this fixed k, the M is called a vector of charge k. So this k denotes this k. So then typical example would be, so let me write this, M could be like 2 wedge 4 wedge 6 wedge 8 wedge 10. The similar thing would be like 0 wedge 4 wedge 6 wedge 8. Right. Just two examples. And later on, I'm going to just be lazy, just write down 0, comma 4, comma 6, comma 8. Oh. So apparently VF is going to be the direct sum of VF upper M and upper K. So this K does denote the charge. So VFK is a subspace of generated by the vectors of charge K. So it's an infinite copies of the same vector space. So the first thing you can observe is like this VF0 is just isomorphic to VP, which is the ring of polynomials. So the correspondence is given by, so here, so it's like so VF0 is parameterized by all partitions. Okay, if you fix a charge, so So this is like the vacuum state, namely everything. There is no space you can insert more. You can insert more factors for this fixing charge. Okay, so this one will correspond to partition empty or zero. This one will basically decrease the first factor by 2. So this one corresponds to partition 1. Am I making sense? So in general, okay. So in general, if I have partition lambda, my notation would be you first take the conjugated partition and you write out the corresponding partition, and the corresponding monomials would be so 2 minus 2 lambda 1, 4 minus 2 lambda 2, and 2k minus 2 lambda k bar, and so on. Let's give you a one-to-one. Yep.
What about the vector 0, wedge 2, wedge 4?
That will be in a different chart, because the chart requires like you have this.
And so you start indexing at 1 or 0 or?
If you use 0 like this, then you will have a vector of charge minus 1. If you translate, you basically translate this subscript, this upper superscript.
Okay. So the first index is called M1, not M0. Good.
Yeah, I call M1. I call M. Sorry, I call M.
Yeah. Okay.
Any more questions?
I'm okay.
Okay. So this is just a one-to-one correspondence between partitions, and this is semi-infinite monomial. Okay. And once you have partitions, so for each partition you can map to the Schur functions in the symmetric algebra. Then you have a linear isomorphism of vector space. Okay, so this is a vector space, VF, and now I'm going to tell you how Clifford algebra acting on this. So my Clifford algebra is algebra generated by AI. I is all integers subject to the relation. So AI, AJ, supercommutator, which means this AI, AJ plus AJ, AI. So it's going to be 0 or 1. So if J is I plus minus 1 and otherwise. So only if like their indices are adjacent, their super bracket is 1. Otherwise it's 0. Okay. So how this Clifford algebra acting on the VF? So now I'm gonna discriminate between the even indices and the odd indices. So basically, so now I'm having how CL acting on VF. So A2I is operator just the wedging 2I. Okay. So because if you wedge twice, you got 0. So that's why AI super bracket is 0. So what is A2I plus 1? So this is called wedge operator. This is called contracting operator in the Clifford case. So A2I minus 1 will be, so you use 2I contraction plus you use 2I plus 2 contraction. So originally the Clifford algebra is just the psi and the psi star. Psi is wedging I, psi star is contracting by I. So you only have psi star, the super commutator is 1. And now I'm doing this like odd and even. So for each one, there is 2 generators such that you have non-trivial pair. Okay? Because of this is plus. So 2 is just by, if A2, so for instance, so if this is M, so A0 acting on M will be the sequence 0, 2, 4, 6, and so on. And if you use like A1 acting on M, it's contraction by 0 and 2. There is no 0, you only have 2. So this one will be 4, 6, 8, and so on. Okay. So then it's easy to check those two operators defines your linear action of this Clifford algebra on the Fock space. So note that the generator gonna change the charge by +1 or -1. So now the categorical story. So we wanna have some monoidal category such that there are some distinct object lifting AI and satisfy this quadratic relation. That's the formal goal. So this is like motivation from the notion of contact category due to Honda. So this is some categorical way to study contact topology in the three-dimensional case. So in general, the category can be defined for any oriented surface. So sigma will be oriented surface, and F will be a collection of marker point on the boundary of the surface. So I won't give you the full definition of this category. So in our case, we just look at some local. So let me first give you the local behavior. So let's think about the surface to be a disk, and you have 6 boundary points along the boundary. So this is a category. What the object looks like. So the object just some crossing these matchings of 6 points on the boundary, possibly with some like contractible loop. So this is object. So object is some isotopic classes of crossing these matchings. Of 6 points along the boundary of E2 plus some loop. So this is a typical object, and then then there are going to be some other objects. So if you have a 6 boundary point, then you're going to have like 5 isotopic classes of objects. This is just a Kessler number. Right? I mean, by ignoring the loops. Okay. So the first thing I want to tell you, since I won't give you the full definition of what this category looks like, so the thing I just want to say is like this crossing is matching gonna determine some geometric structure called contact structure in the neighborhood of this surface, and the morphism looks like, so the morphism is generated by a three-dimensional geometric structure called contact structure on the sigma cross I with prescribed the dividing sets in the bottom and the top. Okay. But in our case, since our surface is relatively trivial, it's just a combinatorial. So let me just tell you how the morphisms looks like. So the morphisms is compositions of so-called bypass attachment. So you can always chop your contact structure into layers, and the basic block is given by this. So namely, there is one contact structure such that gamma 0 looks like the horizontal line, the gamma 1 looks like this. So combinatorially, you're just connecting the top left to the right corner, and then close out the other. And then you will quickly find there is a symmetry. So because the bypass attachment is like attaching on this short arc, which intersect the three lines transversely. But then you can think like this is just this picture rotate 60 degrees. So you can keep attaching bypass here. Then you're gonna get another picture which looks like this. Right? The rule is each time you attach a bypass, you just go from the top left to the right corner. So now the top left is here, the right corner is here, you just connect from here. And then, of course, you can attach a bypass here, then you will go back to the original object. But actually, this is just shifted by, or rotated by 180 degrees, not 2 pi. So there are also some homotopic gradings in this category, which show that the composition of 3 just shift the homotopic grading by 1. And also, each composition is 0. So this is an example of the exact triangle in this topological category. So I just put some degree shift 1 somewhere. But it depends on the homotopic class of the object. So there are 2 more ingredients I want to tell you about this content category, which is going to be used later. The first one is, so 0 object. So whenever you have a dividing set, something like this, as long as you have a contractile loop, it's going to be isomorphic to 0. Okay? So each such object is isomorphic to 0 object. And the second relation is actually, let me write it here. So this is again a local picture. So suppose you have 6 horizontal lines, you can attach a bypass here, you can also attach a bypass here. Then you have 2 ways to get so if you first attach the first one, and then the second one is isotopic to first attach the second one and then the first one. Okay, so this just says like destroying the bypass just continues. So you have this relation holds in the space of morphisms. So this diagram means this is a morphism from here to here. So this path is a morphism from here to here. This path is also the same, and those 2 morphisms are the same. Okay? So you just need this and this criterion. So now let's play with the diagram. see how I can use this category to categorify to lift this clifford action. Okay, so it's actually easier to first draw the Clifford algebra instead of the Fock space. So now I'm going to write the fancy CL, stand for the Clifford category, which is the fancy C denotes the contact category associated to the surface and the boundary condition. So what's the background? The background is just use infinite string and with infinite many mark points on the boundary. Okay. So then you will have a typical object, looks like everything is horizontal. So this one going to give you the unit object in this category. So because this is an infinite strip, you can put two infinite strips together and horizontally multiply them up. You will end up in the same topological surface. So that's give you the monoidal structure on this category, and this is the unit object in that category. Okay. So now I wanna. So for my Clifford algebra is generated by AI, subject to some quadratic relation. Now I just want the distinguished object lifting the AI, the generator. So now I need maybe some label. So gamma I will simply be is horizontal everywhere else, but is this parallel pair in the height of I. Okay. So I label the this is I minus 1, I minus 2. I label the small interval between two mark points. So I call this object gamma I. So my claim is that if you pass to the K0, this one will look like an identity, and this one will look like A sub I. Okay? So what's the relation I have to check? So the first one is AI times AI is 0. This is the one relation in my Clifford algebra. So namely, you just want to put two gamma I together. Okay? So once you have two gamma I, you will quickly find there is a contractual loop, and by that axiom, this is 0 object. So in the quantity group, it will be 0. So that's a way to categorify AI times AI equal to 0. And the most important relation, which is AI plus 1 plus AI plus 1, AI is equal to identity. Okay? So that will simply just like this picture. So let me just draw this here. So what is AI? AI plus 1. So you have some I and then I plus 1. Okay. This is local, just non-trivial things happen between the height of layer I and the layer I plus 1. So this is the object gamma I multiplied by gamma I plus 1. Right? So you can see like by ignoring all the horizontal strand, you will end up with the same picture like this. So if this is gamma I plus 1, this will be gamma I plus 1I, and this is identity. If there is a distinct triangle, all the three terms add up to 1 up to psi. So that's the way to categorify this relation. Okay. So now how about the Fock space representation? So now I will draw curly F, which is supposed to categorify the fermionic Fock space. So this one is again a contact category over some other surface. Now the surface is still infinite straight, but you change the boundary conditions. So you just have infinite many points on the left and only one point on the right. So the categorical action is given by just glue in the dividing side on the Yin strip from the left on this. Right? So it won't change the topology of this underlying surface. Okay. So here, so there is object called 2, 4, 6, and so on. This is a vacuum state of charge 0. So what this object looks like. So I'm gonna just give you. So this is 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, and so on. So I'm claiming this object behavior likes this vacuum state in the ground plane. Okay? So why this is like 2, 4, 6, 8, and so on. So what's the property of this vector is annihilated by A2i for bigger than 2. Right? Namely, if you multiply A2 from the left or A4, you will kill this object. So now you have this like half loop on the left in the position of 2, 4, 6. So if you multiply by something called gamma 2, you will have a contractible loop again. That will give you 0. Right? Similarly, if you're acting A minus 1 for this object, remember A minus 1 is a contraction of 0 and minus 2. Right? So there is no 0, no minus 2, which means A minus 1 also kills this object. And if you add A minus 1, there are also another half loop here. So it will kill this object. So the claim will be this object. So if I call this is M, so this one will be the categorification of this M. Okay. So now let's see what can you this category looks like. I mean, starting from this object, what kind of bypass attachment you can attach. So remember, bypass attachment is just some little short arc which intersects 3 horizontal lines locally. Right? So by attaching this, so now we just localize on this picture, and you can see so this will be the resulting configuration. So namely, this is 0, 1, 2, minus 1, minus 2. 3 and 4. So my the bypass attachment, the local picture, if I embed this into this big picture, tells you there is a morphism from here to here. Okay. And what this object looks like in the semi-monomial basis, so it's going to be, looks like 0, 4, 6, 8, and 4. Right? So you just have to observe like which half circles in the even integers. So you have 0, you have 4, and so on. Okay. So this is at least I tell you the first two configurations. In this category. And now let me just ignore some like computations, tells you what's the result at the end. So now I go back to the partition notation. So the vacuum state corresponds to 0 partition, and the next one corresponds to partition of 1. And in the layer 2, you have partition 2 and the partition 1 squared. And then you can go further, right? So this bypass attachment just gives you this morphism. So this picture is just this picture. And then you can keep going by attaching bypass on this. We're going to resolve on the other two. Yeah.
Is that the only bypass attachment you can do that gives a non?
That's the only non-trivial bypass.
So,
other non-trivial bypass will affect through this. So for instance, you can also attach something like this, right?
Uh-huh.
This one will affect through this. So the second bypass will be this morphism. This is like a minimal bypass you can attach starting from the gamma 0.
Can you say again how how one of these sequences of integers gives a diagram? Can you do?
So
one more example.
since I only use even integers, right? So here this diagram corresponds to 2, 4, 6, 8 because I have a half circle in the location of 2, 4, 6, and so on.
Can you do another example? Sorry.
So wherever the half circles are, that's the thing.
Sorry?
I was just repeating what you said about the half circles forming the list.
If there's two nested things, it means you skip a number.
So you can look at the difference between those two things. You only find where you have half circles in the even integer. So in this picture, you have half circles in the position of 2, 4, 6, and so on, right? You ignore all the -1, -3, and so on. So this one going to result in you 2, vec 4, vec 6, vec 8. And then if you check this, 0, 4, 6, and so on are the only even integers where you have this half circle. Let's give you 0, vec 4, vec 6, vec 8. Okay, so yeah, since I don't have too much time, I'm just okay. You can continue attaching bypass. The resulting category looks like okay. So the resulting category looks like a module over some quiver algebra I call R, and you probably go to like the homotopy category of projective modules. And R is the quiver algebra associated with a quiver where, so R is the quiver algebra mod of some relation. So where Q, the vertices just equal to all the partitions. And arrow, you have one arrow if lambda is a subpartition of mu, and their size differ by 1. So it's basically just the induction quiver of the symmetric group. And the relations sorry, how to make it? Okay. So the relations, there are two relations. So one is once you have a different path from partition to a partition plus 2, you have two classes, then take a mu. Okay. The second one is from 0 to 1 squared. This is equal to 0. Okay. So the relation will be lambda to mu to eta is 0 if eta. So this is 1 squared. So you cannot go twice in some direction. And the other one is if you have this pair, then they commute. You just have this quiver algebra and the model of these two set of relations. And you're resulting the algebra I call it R. And this is topological motivation, and the algebraic framework is just to compute like this category. This is the categorification of the Fock space, and you look at certain bimodules over this category. Okay? Give you the Clifford generator. Yeah.
I'm curious, does the contact category make sense if it were on an annulus? Like,
Yes.
because it seems like this is like SL infinity version, and then there's like a affine SL inversion if you took maybe like the contact category on an annulus and did the similar thing?
I only computed the annular version with finite many boundary points.
Yeah, with finitely many boundaries.
Yeah. But this one you require infinite many.
Right. Like I was just saying, like this is like affine or SL infinity, and then.
The annulus, it looks like more like a GL11.
Oh.
Yeah, some affine version of it. Because whenever you have a generator AI squared equals 0. That more looks like GL11. Okay, so this is the Clifford side. Now what's the corresponding Heisenberg side? So now you can forget about the contact topology, just remember this is the equivalent very interesting. So what's the Heisenberg side? So recall, like Khovanov's Heisenberg category acting on the direct sum of symmetric groups. So if you draw the quiver of the representation category of this one, it just looks like you have all partitions without any error, because each partition gives you an irreducible representation, right? You have no error. So which means now we are doing some modification of Michael's Heisenberg categorification. Then we will add some arrows and the relation. So now, this is right. So how to see the arrows from the Heisenberg side? So for the symmetric group, we'll just use some like strands, and then you have the symmetric group action. So for this morphism is a morphism from 0 strand to 1 strand. So I'm just adding one more generator is a half strand. So this one denotes morphism from 0 to 1. Okay. So this new ingredient corresponds to this bypass attachment. So now you have to set up the relation. So the relation is simply just the half strand can always pass through the symmetric group. Okay. Why you want to set up this? Because remember we have this relation. If you go the direction down twice, you got 0. Right? So a particular case of this will be from 0 to 1 to 1 square. This composition is 0. So in our case, what is this? So from 0 to 1 is here. And from 1 to 2, you can either draw this, and I put a symmetrizer here, where this symmetrizer is like 1/2, 1 minus identity. Is this okay? Okay. So if I want to compose, I will get something like this. This is the composition. So if you compute, this is 1/2. This guy, or maybe this one. With this, and now the relation tells you the half strand can always going through. After going through, it's just a homotopy of the same diagram. So the result of this is 0. So in the contact topology, there is a relation from here to here 0. On the symmetric group side, then you just add this generator and add this relation. Okay. So by adding those, I can define some like just some extension of this symmetric group. I call it algebra B, and then you can show the algebra B is Morita equivalent to the algebra R. So then you basically use the category of projective modules over B to categorize the bosonic Fock space. So B projective module, maybe KB, then will be equivalent to KB of R projective module. And then if you take K naught, this will give you VB. If you take K naught, this will be F0. Okay. So the equivalence of categories is induced by Morita equivalence. And now, what's the corresponding Heisenberg action? So to distinguish with Michael's H, I call like EH. So we need just the induction functor and the restriction functor. Okay? So I will just draw this diagrammatically. P will be some bimodule looks like this. And Q will be some bimodule looks like this. So when I draw this a little bar, I mean this strand is frozen, namely you cannot act on this strand. Same for this. So this is induction functor, this is restriction functor. So now I'm going to quickly review the properties of this Heisenberg category compared to the Michael's Heisenberg category. So first of all, you have this Heisenberg relation. So this is, I'm working over the bimodule over P. So you have like QP, Q tensor P is 1 over some PQ. This is Heisenberg relation. And also you have the P is left adjoint to Q. Q is right adjoint to P. But now, since the category, the algebra B is not semi-simple, so you don't expect P is actually the right adjoint of P. So there is no bi-adjoint. This is adjoint pair. So, but actually, I can find something like I can find an infinite family of bimodules or complex of bimodules to complete this adjoint pair. So namely, I can find some bimodules which is right adjoint of Q. So the definition of P1 is actually the cone from identity to P, and the morphism is given by F0. So what's the F0 looks like? So F0 is from the identity functor, which is the module itself, to the bimodule P. So diagrammatically, I just sum any diagram to this box means there is some diagram inside. I just go to this diagram. Since now you have the half strand. So this is F0. You actually have infinite many morphisms from B to P. And so for Q1, I just mentioned this Q1 is an extension of the identity functor to Q. So you have a family of this adjoint functor, which is also expected from the Clifford picture. So in the last 5 minutes, I want to tell you about something about the.
Do you have a diagrammatic presentation of the entire category EH?
EH?
Yeah.
No, because it's triangulated. I don't know how to handle the extension. I mean non-homological. Even for the bimodule category, it's not easy to compute the dimension of the Helms group. Okay, so finally, vertex operator. So I want to just focus on the So you can form some like generating series out of the Clifford generator. So I call it A. So I call it AZ, which is A2I Z to the power -I, and A bar Z, which is A2I plus 1 Z to the I. Okay. So then I want to see, maybe let's focus on A bar. So I want to define Sn, which is T tensor your sum -1 to the power I A2I plus 1, and I is from the -infinity to from the -infinity to n. Okay, this is Sn bar. Okay. So basically, I want to categorify those two operators, and I first evaluated z at -1. Then I have alternating sum of Clifford generator, and since it's an infinite sum, I take some finite truncation up to n. This is subscript n. And remember, each Clifford generator will change the charge of the vector by 1. So I use the translation back. Okay, so this is a linear operator acting on Vf0. Okay. So T is a translation between different charges. So my claim is that there is an unknown functor of the category B of the category R projective modules, such that if you descend to the Grothendieck group, it looks like Sn. So again, you need some like filtrations of the infinite dimensional algebra R. Okay, so for S bar, so now look at this. A family of subalgebras of R, which is generated by partitions with at most n columns. You just find some filtrations of the algebra R. Okay, so the theorem will be, this is called Rn bar. Okay. So the D of Rn bar is the linear dual of the algebra, and then this is the bimodule over Rn bar, and I use the bimodule derived tensor product, and this is the functor from the KB Rn projective module to itself. So the theorem is define that. I call it Sn bar curly K0 of Sn bar is the same as Sn bar. So if you let n go to infinity, I can more or less say I categorify those two operators at the value z equals -1. Okay, yeah, I think I just want to stop here. Thank you.
Are there any questions?
Can you compute natural transformations of these functors?
Natural transformation of what?
Of,
You mean this one?
yeah.
How to compute this?
Yeah, I mean, do the natural transformations match what you see in EH?
Or in H? You mean write this in term in the Heisenberg side?
Yeah.
I don't know. This is Clifford side because this generating series is Clifford.
Oh, yeah.
Any other questions? Oh, yeah.
So is this even that the K theory of EH is the Heisenberg algebra?
The K theory of the EH is what?
The
Heisenberg algebra? Oh, it's a conjecture only.
Okay.
Yeah. It's hard to compute the cable.
Yeah.
I'm more focusing on how to lift the series into functors.
And
Yeah.
So your combinatorial version of the contact category is basically Young's lattice with like, well, is that a triangulated category or
It
I was
is.
kind of confused by that. So you
It is a triangulated category.
do you define it combinatorially then, or
In this case, you could, but once your surface is genus, then it's not. You have to pass through some like DG algebras, like in the floor here.
Any other question? And I think we have a coffee break, but before things again.
Okay, thank you.